Hello, my name is Jace, and it's my turn to do the video explanation, specifically for Chapter 23, Question 3 of the paper homework. So our problem statement is that we have an infinite thin straight wire that has a positive charge distribution of lambda. So part A says to create a three-dimensional situation diagram showing the electric field generated. So this is our infinite wire. Our electric field is going to point away from the wire at 90 degrees in the Z, X, and Y axis. We have even more electric field vectors that are pointing at a 45, but they're always pointing directly away from the wire. So for B, we have used a finite cylinder as a Gaussian surface of length L and Gauss's law to show that the electric field created by the wire at a radial distance from the wire has a magnitude of E is equal to lambda over 2 pi epsilon naught r. So we're going to draw a situational diagram of a Gaussian surface along the wire. The two most important things, we're going to have three integrals because we have three different surfaces pretty much. We have circle 1, circle 2, and then the sides of the cylinder of the Gaussian surface. We're going to need to find theta for all the surfaces. So for the two circles, first is going to be the angle between the normal vector to the circle and then the electric field. This is the normal vector of the circle. It's going to be pointing parallel to the wire that is coming out of, which means that the angle between the electric field and the normal vector of the circle is equal to 90 degrees. And then using the definition of the dot product, cosine of 90 degrees is equal to 0. So both of our integrals for circle 1 and circle 2 are going to be 0. This is not the case, however, for the sides of the cylinder right here. We can see that the electric field and the normal vector, which will be pointing in the same direction and parallel to each other, meaning that we have an angle of 0 degrees. So cosine of 0 degrees is equal to 1, so the cosine disappears. So now that we established what kind of is happening first, we're going to use Gauss's law. This is going to be the closed integral of the dot product of the electric field, and the area is equal to Qn over epsilon naught. So we break it up into our three different integrals, the sides, circle 1 and circle 2. These two circles go to 0, and then we just have this integral. Cosine of 0 goes to 1, so then we just have, and our electric field is constant, so we can pull that out of the integral. So then we just have the integral of dA, which is just equal to A, and then the area of just the sides of the cylinder is equal to 2 pi r L. And then this whole thing is equal to Qn over epsilon naught. We're able to pull out the epsilon naught, and we're able to pull out Qn over L, and that is equal to lambda. So we turn the Qn over L into lambda, and then divide 2 pi r over under lambda to get it next to the epsilon naught, and then we have the electric field at a radial distance away from the wire of a cylindrical Gaussian surface is equal to lambda over 2 pi r epsilon naught, which is equivalent to the problem statement. Thank you.